哦，对，有人在群里打广告了。对啊，好的。我看到有人去了，还朋友圈。对，那个看起来真的很好。那个叫什么？但是那个
continue with context-free languages and context-free grammars. So we just proved some theorems, closure properties, and a couple of non-closure properties. Any questions about any of these? So let's talk about decidable properties of context-free languages or context-free grammars or push-down automata. So similarly to what we talked about finite automata, right? Given a finite automata and a string, does it recognize that string? What's the algorithm for? Simulation, right? Or whether the languages of two finite automata were the same language, have algorithms for that. Whether a language represented by a finite automata is empty or not, we have algorithms for that, and so on. So is the language of a PDA empty? Is its language finite? Is its language infinite? Right? Is a particular string an element of that language? Right? So you can have algorithms for some of these things. For example, whether a string is a given, whether a string is in the language of a particular PDA or whether a string is generated by a particular grammar, how would you determine that? If I give you a string and a push-down automata, and I say, is that string accepted by this push-down automata? How could you tell? What's your algorithm? One word.
Check.
Check. How would you check? Simulate. Simulate the PDA on the string and follow its operation, and then you'll know what it does at the end. What if it's non-deterministic and it branches multiple different directions? Every character, you have non-determinism going and lots of branching. What do you do during the checking process? Not hard.
Could it be transforming to deterministic?
But we can't do that in general. Remember, some context-free languages are not deterministic.
Right.
Non-determinism is essential.
Just keep track of all.
Keep track of all of them. Check all of them. Check all the ways it bifurcates. How many roughly will there be as a function of the length of the string in the worst case? Exponential. That's okay. I never said be efficient. I just said do it. Because some things cannot be done, even inefficiently. The whole big problem cannot be solved even inefficiently. Even with exponential or super duper exponential argument, the whole big problem cannot be solved. Not even very slowly. So it's not for granted that we can take any more, that everything can be done even inefficiently. Some things cannot even be done inefficiently, never mind efficiently. If I say, here's a grammar, is this string an element of the language generated by this grammar? How will you check that?
By producing it?
By producing that string or attempting to produce that string. And you can follow all derivations of a certain length, the length of a string or less. And there's only a finite number, an exponential number, a large number, but only a finite number. And eventually you'll get it, if it's possible. There's a name for this problem of given a string and a grammar, whether that grammar can produce that string, whether that string is an element of the language induced by that grammar. It's a famous problem, there's a name for it. What is it? I'll give you a hint. You've all done it hundreds of times in the last few years. You've all solved that problem hundreds of times. Compiling. It's called parsing. Or compiling, if you will. How many get that? What is that string in the context of parsing or compiling? What does that string stand for or represent? Your source code. What is the grammar?
The language that we have.
The syntax of the programming language. All the rules that make valid programs in terms of statements and syntax and so on. And the answer of whether that string is an element of the language produced by the grammar of the programming environment or programming language is parsing or compiling, determining whether it's a valid program, whether it has syntax errors or not. Any questions about that? And I'll let you ponder about the other ones. For extra credit, prove to me the other ones. Try to figure out algorithms, whether the language of a given machine or grammar is empty, whether it's finite, whether it's infinite. So this kind of parallels the questions we asked about finite automata. I remember the finite automata version of these questions just last lecture. Okay, now, but here are some undecidable questions about push-down automata and context-free grammars, just so you don't think everything is doable. For the following, no algorithm exists. If I ask you, is this push-down automata minimal? Minimal. Is it the smallest possible that does this job, that recognizes this language? Undecidable. You can prove that too. If I give you two PDAs and ask you, do they accept the same language? Are they equivalent? Undecidable. These were decidable for finite automata. How many remember that? How would you find if a finite automata is minimal, the smallest possible?
You can't minimize it, for example.
Run it through Hopcroft's minimization algorithm from 1970, n log n time. If you don't get anything smaller, you know that it was the smallest, right, for deterministic finite automata. How would you determine two finite automatas are the same, recognize the same language? Not PDAs, but now finite automatas from 50 slides ago. Remember that?
We did the regular expression minimization can be, it's decidable,
It's decidable.
but it's
The intersection.
Intersection. Take the difference of M1 and M2 and M2 and M1, and the differences should both be empty. And if both are empty, it's a different only if they're equivalent, they recognize the same. How many remember that proof? Okay, good. For PDAs, you can't do that. It won't work.
because intersection is
So it's undecidable also. If I give you context-free grammar and I say, is it the minimum grammar? Is that the least number of variables or the smallest number of productions or the least number of characters to represent the whole thing? Undecidable. There's no general way to compute that or determine that. If I ask you if a grammar is ambiguous, undecidable. If I ask you the language of one grammar is the same as the language of another grammar, undecidable. And you can prove all these things, right? So for extra credit, maybe prove some of these things are undecidable. Pick some of your favorites. The intersection of two grammars, the languages of two grammars intersected, whether it's empty or not, whether they have anything in common, any string accepted by both grammars, undecidable. Whether a language is inherently ambiguous, undecidable. So for extra credit, I leave some of these to you because we have to get into other things. Any questions about any of this? So this is where things get more difficult in terms of what can and cannot be done, what can be decided or computed, and what can't be. Question?
Like to prove any one of these, is it always reducing to the halting problem?
Most of it, yeah. Most of it is reduction from the halting problem. Or something equivalent to that. Yeah. So look in the book for some examples and prove some for yourself.
A question.
Yeah.
What's the definition of minimum?
Definition of
Minimum.
minimum? Oh, minimum smallest number of productions, or smallest possible number of variables in the grammar, or the total description in terms of characters representing all the productions of the grammar. It's one big string, right, including carriage returns. So you could take any one of those definitions to be the minimum. They're all undecidable, whether a grammar is minimal under any one of those metrics. Finite automata. So that's for grammars. For PDAs, smallest number of states, let's say. Or if you prefer, smallest number of states plus transitions. However you want to think about it. But let's say smallest number of states. Undecidable. All right, let's talk about potential enhancements to PDAs. Because for finite automata, if we enhance finite automata in certain ways, you will get more recognition power. For example, take a finite automata and give it a stack. All of a sudden, you can recognize languages that you couldn't recognize before. Now you have a PDA. Or if you have finite automata and you give it two heads, so on the input, it has two heads that can move independently on the input. Now this finite automata, no stack, this finite automata can recognize languages which are not regular, which you couldn't recognize before. For example, what? 0 to the n, 1 to the n. You can recognize that with two heads. How many can see that? How would you do that with two heads?
Should the first head to give the 1 and
Yeah, leave one head alone and on the zero, on the beginning of the zeros, and put the other head on the beginning of the ones, and then move them in lockstep, checking off a 0 against the 1 every time. And when you run out of zeros, exactly when you run out of ones, you accept, and you have to use the stack. How do you get that? Yeah. Any questions about that? So 2 heads are better than 1 is what we just proved. Right? You know the old saying, 2 heads are better than 1? Well, now you know why. Literally, it's true. It's a theorem. But for two-way finite automata can move its single head back and forth. That's no better than a single head. That can buy you any more recognition power. For extra credit, I asked you to prove that, I think. Now, for two-way PDAs, they're more powerful than one-way PDAs. If you can move the read-write head, or I guess it's just a read head because it doesn't write, onto the input back and forth, to the left and to the right. So you can move on the input this way, then you can move back the other way, then you can move this way based on which state you're in and what you're seeing in the input. You can move in both directions. You can recognize new things if you're a PDA. Why is that true? How would you prove that? What's the proof technique?
Again, you can take 0 part and 1 part and 2 part.
And what's the proof technique for that?
Simulator, example.
Example. We'll give an example of something that you can do with a two-way head that you cannot do with a one-way head, just going one direction. And this will be an example right here. Right? And that's not context-free, we already said that, but if you have two-way head, compare the zeros against the ones using the stack. Push the zeros on the stack, pop them against the ones, then you'll know that zeros and ones happen in equal numbers. Then what?
Use the same head to point out to check whether it is.
Use the same head to check the ones against the two, but the head is already here.
No, you can move 0 and 2 together to find whether it's the same and.
No, you just have one head.
Move the head.
But you have one stack.
Move the head backwards.
To the middle between last 0 and first one.
Right after the zero, and then check the ones against the twos. Use the same technique with a stack. Flush the stack, put the ones on the stack, pop them against the twos,
Yeah.
and then you'll know. Because you check the zeros against the ones, make sure they're an equal number. Then you check the ones against the twos, make sure they're an equal number. And now you know all three are an equal number because of what?
Transitivity.
Transitivity of equality. There's a good reason for everything, you see. And now you've recognized this with a single stack, with a single head that moves back and forth. Of course, you can also recognize this with two heads all moving in the same direction, right? Move one head here, right? Match the zeros against the ones. And then when one head is here and one head is here, match the ones against the twos. And for that, you don't even need a stack. Remember, finite automata could do that. But certainly, if you have two heads with a PDA, it's better than one head with a PDA. In fact, even a finite automata with two heads can get more power of recognition, right? So we already found examples of non-context-free languages accepted by a two-way PDA or by a two-headed PDA, right? Now, what if you have two stacks? If you have one stack and another stack?
Same language. The same
Right.
language is it.
Same language can be recognized using two stacks and one head, moving one way. Right? How would you recognize the same language using two stacks?
Push it on both stacks.
Right? You have one stack and you have another stack.
Push both stacks.
Push all the zeros here, push all the ones here,
Pop both.
and then pop both against the twos, and then you'll know that they're all at equal numbers. How many get that? Pretty straightforward, right? So two stacks are better than one. And we just gave an example of that. So you're getting a lot of mileage out of this language. You can use it in also, this language in all sorts of scenarios or variations of this language in all sorts of scenarios. So keep this language in mind. It's a powerful tool. If you have one cube, not a stack but a cube, that's more power. Yeah.
So stack PDA equivalent to Turing machine?
Yes. So since you mentioned it, two stacks are equivalent to a Turing machine. So it's not just more powerful than a one-stack PDA, it's as powerful as an arbitrary Turing machine. You can use the slinky construction, this slinky toy like this. Whenever you push, you pop onto this stack, you push onto this stack, and vice versa, which means you can go through the entire contents of the stack without losing it. You just push it onto the other stack, see what's in the middle, and then push it all back, and now you know what's in the middle. Remember in your statement and transition accordingly, and you can do that every time you need to move in the middle of the stack. So essentially you have a tape now. How many get this idea? And later we'll talk more about that. But yeah, 2 stacks is a powerful Turing machine. Good comment. Any other thoughts or comments so far? Okay. So if you have a queue, that's more powerful than a stack. How would you recognize, for example, this language with a single queue? So you have a queue, so you can push here and pop from there. That's similar, right? So push the zeros onto the stack. So now you have n zeros on the stack. And just for good measure, put a $sign, at the end. So you know where the end of the queue is. So you put an extra character. It doesn't have to be $sign. It could be a pound sign, a euro sign, a yen sign. Choose your favorite symbol. It's around 0. And now what? Push all the zeros onto the queue.
When you add 1,
Yeah, and then every time you see a 1,
you remove a 0.
pop a 0 and push it back on the top. So first you'll pop the $sign and put it here, so you know where one starts and one ends, right? And then you'll pop this 0 and put it there. And you're cycling the queue, basically. Cycling it completely. And when you cycle it one whole time against the ones that you see in the input, all the zeros are still preserved on the stack. There's n of them there. And you know where it ends because you'll see the $sign of them down here. And then you can start comparing that against the 2s. So by transitive equality, all 1s, 0s, and 2s are all in equal numbers now. And you check this language and accepted it, and nothing else. So a queue is better than a stack. In fact, a queue is as good as a Turing tape. A single queue is as powerful as a Turing machine. We haven't talked about Turing machines specifically yet, but you can imagine how this can simulate an arbitrary tape, not just a stack. Because you can access the whole stack and everything in the middle without losing the stack by cycling it one whole way around. Intuitively, that always works, and it's general. 2-head PDAs we already talked about. They're more powerful because they recognize this language, right? And non-determinism increases the power of PDAs. That one is harder to prove, but this language WWR, palindromes, that's recognizable by a non-deterministic PDA, but not by a deterministic PDA. So let's talk about how a non-deterministic PDA will recognize WWR. How would you do it? How would you recognize WWR with a non-deterministic PDA? Yeah.
So if you know where the middle, if you know what W is already, you could do it with a deterministic one, but since you don't know.
Yeah. So if it was the language W $sign WR, that's different. That is deterministic context. How would you recognize W $sign WR?
Until you find the delimiter, you can still push it into the stack.
Yeah, take the W and push it onto the stack. So now the W is on the stack reversed, because you push it first character last, and the last character will be here. So it'll be the last character here and the first character here. And then just compare it to the WR that's following the $sign. And then you'll know. How many understand that? It's pretty straightforward. But if the $sign isn't there, that's a trick. That's hard to do now. Harder to say. What must you do, not deterministically, because there's no way to do it deterministically. You don't know what the middle is. So what can you do? Non-deterministically do what? So keep pushing the W. So push and push and push and push the W.
In one.
And
pop,
until
keep
when?
popping in another thing you can keep popping until you reach the end of the
Yeah,
string.
so in some sense you're guessing where the middle is. After every character you push, you assume that's the middle of the string now, because you don't know. You don't know if the string is 2 more characters, 100 more characters, 1 billion, 1 trillion, a Googleplex more characters. You don't know. You're not seeing the rest of it. All you're seeing is the character that you're pointing to right now. So guess that the next character now is the other half, that you just pass the middle. And start the popping process like you did with the $sign in the middle. Start the checking process, checking the W pushed reversely onto the stack against the WR reversed coming in the rest of the input. And if it matches 1 to 1, you know you guessed the middle right. But what if you didn't guess the middle right and you were wrong? Most of the time you'll be wrong because you're guessing that middle every single time you make a move. You guess that it's either continuing with a W or starting with a WR.
We just need 1 to succeed.
Yeah, as long as you guess correctly once, you're good because the check will confirm that you were right. And you didn't have too many W characters or WR characters because you guessed correctly. All those wrong guesses, it's the cost of doing business. Venture capitalist model of computation. You can be wrong a lot as you deterministically computing. As long as you're right once, the whole thing is good. You found a Facebook or a Google investment. That's good. How many get this? So that's a non-deterministic algorithm to compute WWR or to recognize WWR. And you can also prove separately that no deterministic mechanism can do this. No deterministic PDA can do this. That's hard to prove because you have to prove that you're not a millionaire. So we showed how a deterministic mechanism can do this, but to show that no deterministic mechanism can do this, PDA, push automata can do this, that's a bit of a trick and that's harder to do. But you know, you can prove that too. For extra credit, maybe give me the proof for that. Okay, so that's 5 more theorems. Any questions about any of those? Yeah.
So I was wondering if the two-way PDAs are more powerful than the two-stack. Like, what's the relationship between all of these? Are they comparable?
So a 2-stack PDA is as powerful as a Turing machine. So that's the ultimate power. Right, because you can show, I think some of the homework problem, or some of the upcoming homework problems or problem set problems, will ask you to show that 2 stacks are equivalent to a Turing tape, or at least that they have ultimate power of recognition. A 2-way PDA is not quite as powerful as a Turing machine, but again, I'll leave that characterization. I'll be somewhere in the middle. More powerful than a regular PDA, but not as powerful as a Turing machine, because you still don't have an arbitrary tape. But you can recognize things like 0 to the n, 1 to the n, 2 to the n, for example, in other non-context-free languages. So I'm saying it's extra credit, but we really proved most of them right here. So, any other questions about any of this? Okay. So in terms of the book, we're right around page 77, 79. We're going back to the section on regular languages, even though the context-free languages are the next chapter, chapter 2. I want to show you something about regular languages and something about the pumping lemma, or the pumping theorem, really. How to prove that certain languages are not regular. So we already mentioned that if you have a language that looks like 0 to the n, 1 to the n, it's not regular. This is going to be a little subtle. So this is not regular. Not regular, but it's context-free, but not regular. Now, why is this context-free? Because you can recognize it using a stack. Push all the zeros, pop against the ones. You're good. Well, why isn't it regular? Well, let me give you a non-proof, and you tell me why it's not a proof. I'm going to say, okay, it's not regular because you don't have a stack, so you can't push the zeros and pop against the ones. Why is that a non-proof? Maybe you can do it without a stack. Let me give you an example of another language that you can do with a stack, but you can also do without a stack. Because here each string has equal numbers of zeros and ones, and they must alternate. You must have a 0, then a 1, then a 0, then a 1, but in equal numbers. So they must alternate like this. You can do it using a stack. Right? Count the zeros. Right? And pop against the ones using a stack. For every 0 you push onto the stack, you see 1, you pop it against So that uses a stack to make sure there's equal numbers of zeros and ones, and that they alternate. How many get that? So I used a PDA to do that, which means it's a context-free language. But I can also use it, compute this language or recognize this language without using a stack. How? It's a regular language because it's 0 star, it's 0, 1, parentheses, star. Right? So a two-state finite automata will recognize 0, 1, 0, 1, 0, 1, two states. How many get that? Okay. So just because you can use a stack to recognize something doesn't mean you can not recognize it without using a stack. Right? I mean, all of life is like this, right? I mean, just because you can solve a problem using your fists doesn't mean you can't solve it without using your fists, right? Or violence in general. So it's a non-proof to say, well, you can solve this using a stack, and therefore it's not regular. All right. What about if I said, you need to somehow count the zeros and then count the ones, and compare the counts, and the finite automata has nowhere to count. It has no counter or no place to store arbitrary large values. That's true. But I could say the same thing about the 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. Count the zeros and count the ones, compare the two counts. That's not the only way to do it. You're not using two-state finite automata without counting, just computing parity as you go. So those are non-proofs. It is actually not easy to prove that this is not regular. The finite automata cannot possibly do this job. No finite automata in the universe can recognize this language. We're about to prove this rigorously. So let's say a couple other things first. So all regular languages are context-free. How many believe that? A regular language necessarily is also context-free. How many believe that? Okay. There's only a third of the class there, so that's a pretty straightforward one. Why is that true?
It's the same as a PDA without a stack.
Yeah, a regular language can be recognized by finite automata. Finite automata is a PDA that doesn't use its stack. That's okay. You don't have to use your stack if you're a PDA. So a regular language is necessarily context-free. Is a context-free language necessarily regular? No, of course not. Or you see examples over here that some context-free languages are not regular. Right? So some context-free languages are not regular, right? And let's go over this argument here. So I'm going to give it to you in symbolic logic here. And that's a mouthful. So before we dissect this statement down here, let's kind of wrap our minds around the intuition. So let's say you're a finite automata, and you're trying to recognize something of this form. So you're trying to recognize a bunch of zeros followed by a bunch of ones in equal number, trying to recognize something like this, 0, 0, 0, 0, 6 zeros and then 6 ones. You don't like 6, make it 100 zeros, 100 ones. Let's say you're a finite automata, you're trying to recognize, suppose you're a finite automata to recognize these kind of strings and only these kind of strings, and those are the only ones you accept. So starting here, you keep changing states. You're a finite automata, you change to this state, then you change to that state, then you change to this state. So I'm changing states, state to state to state, as I go over the zeros. But there's a lot of zeros, more zeros than I have states. I'm a finite automata that supposedly recognizes this language 0 to the n, 1 to the n. So there's more zeros in here than I have states. And that must be true for some of the strings that I'm supposedly accepting. Why? Because I only have a fixed number of states. I can have 13 states or 1 billion states, but that's it. I'm fixed finite automata that recognizes this language. This language has larger and larger strings for larger and larger n. And eventually this n will exceed the number of states that I have. And if I still try to recognize such a language with such strings for large n, eventually there'll be more zeros than I have states. How many believe that? Why is that true? And if it is true, what must happen to me as I keep changing states, and I'm still looking at the zeros, and I keep changing state to state to state, but there's more zeros than states. What will happen to me in terms of these states? What can you say that's not trivial about the way I'm changing states? If there's more zeros than states that I have, it's not a trick question, but it's not completely vacuous observation either. I will eventually repeat the same state twice. How many can see that? Just 2 people can see that. Okay. If I keep changing states from state to state to state to state, and I keep making more changes than I have states, because there's more zeros than I have states, eventually I will repeat the same state twice, at least twice. There's a name for that, 2 words. Pigeonhole principle. Good, thank you. Our friend, the pigeonhole principle. We get a lot of mileage out of that too in this class, pigeonhole principle. So let's say I accepted, some portion. So let's say I repeated one of the states. So let's see what happens. I started in a start state. I went to some other state eventually. So this is not necessarily one transition. It's some series of transitions that end me up here. And here I repeated, this is the state that repeated. State, I don't know, Q sub I. That one is repeated. And then from here, I went to some final state and accepted, because I'm supposed to accept this string. So I repeated myself somewhere in the middle here. And eventually from that repetition state, I eventually ended up in a final state after a bunch of other transitions. How many see this is a symbolic representation of what happened in my finite automata control, state control, for recognizing this string? How many see that corresponds? Okay. So let's call this portion U, and this portion we'll call it V, and this portion we'll call it W. The characters along this path collectively will be called the string U. This portion here, this path here, will have the characters along this path collectively called W, the concatenation of all the characters along this path. The concatenation of all the characters along this path will be called V as a string. I'm just labeling those strings U, V, and W. Now, bear in mind there could be lots of other cycles elsewhere. I'm just pointing out this cycle here that must exist by the pigeonhole principle. But it doesn't exclude the existence of other cycles elsewhere. But so it could be lots of cycles here. I'm just going to ignore them for now. So the input string, which is this input was U, V, and W. Right? How many see this representation? And I accepted this as a U, V. I don't know where the U is, where the V is, where the W is, but together, the U and the V and the W are exactly this string of 6 zeros and 6 ones, or N zeros and N ones more generally. How many get that? Okay. Now, the U and the V and the W, the U and the V and the W cause this machine to start at the start state and end up in the final state in this manner. But if I fed it a different string, like U, V, V, W, what would you say the machine will do on the string U, V, V, W? Same thing, you'll accept that too. In fact, you'll accept it, however many V's there are here, you'll still accept all of them. In fact, you'll accept all strings of the form U, V to the I, W, for all I. How many see that? Yeah. So it must accept an infinite number of strings if it accepts one string long enough. How many see that? Now, that's not to say all strings it accepts are in this form. But if it accepts a string long enough of this form, it must accept all these other strings of the form V raised to any power. That's called the pump. That's why it's called the pumping lemma, or the pumping theorem, or the pumping argument, because you pump up the middle portion to any number of times that you like, and it must recognize all such strings also. It has no choice. It's a deterministic finite automata. It has no choice. Once it does something based on one string, if you give it the exact same string again, it'll do the exact same thing again. It won't change its mind. That's what it does. It's a deterministic finite automata. It does the same thing as it did before for the same input. Right? Which means every string that's long enough has this pumpable part in the middle that must be pumped up, and all the resulting pumped up strings must be in the language also. And it must accept those too. So where in this string right here of 6 zeros and 6 ones is this V? This V can be in one of 3 places. It can be only in the zeros, it can be only in the ones, or it can be across the zeros and the ones somewhere. There can only be 1 or 2 or 3 different situations where the pump V can reside in this string. How many can see that? Where else would it be? Only in the zeros, only in the ones, or maybe crossing the boundary. But that's the only 3 classes of situations that you can have. So if the V is only in the zeros, once you pump up the V, you must accept that too. But what's wrong with strings where the V is only in the zeros and the V gets pumped up? Won't be the same number. There'll be too many zeros and not enough ones. And it shouldn't be accepted, but it will from this argument. That's a contradiction. What about if the V then was only in the ones? More ones than zeros, the opposite problem. And it shouldn't accept those, but it will accept those necessarily, because it's deterministic. Then only one last case can possibly save us. What if the V therefore was crossing the zeros and the ones boundary?
It depends. Depends on what V is like.
Well, V is a bunch of zeros and a bunch of ones.
It won't be in order.
They won't be in order. When you pump that up, you get zeros and ones, then more zeros and more ones when you put the next V. When you square it and cube it, you'll get zeros and ones out of order. Right? So, because if V is this, you take V squared, it'll be 3 zeros, 2 ones, 3 zeros, and 2 ones again. It just won't be of this form, and it shouldn't accept, but it will accept if the V was in the middle here, crossing the boundary. So no matter where the V is, it'll create strings that will be accepted but shouldn't be accepted and are not in this language. Which contradicts the assumption that the finite automata accepts this language and it does it correctly. Accepts strings like this and only strings like this. Which means that no finite automata can possibly do this job of recognizing only strings like this. Because if it did, it would accept lots of strings that are not like this, and then it would be doing its job. It's a contradiction. How many see this argument? That's end of proof. Okay. Any questions? This is subtle. Yeah.
Yeah. So I feel that I should be strictly greater than 0, and not B is non-trivial.
Can this I be 0? What if I give it a string of the form U, W, no V, I is 0? Will this U, W get accepted here?
Yes.
How many say yes? Yeah, it will.
Okay.
Good question. So it could be equal to 0. And that's why I very deliberately have this equal to here. I could be equal to 0. It's very intentional. It's good that you caught that, yeah.
So we have only one loop here, the V, right? Is it possible for us to have multiple loops?
Oh, you can have lots of loops. In fact, this loop can have loops around it. You know, you have loops inside loops, sure. But all I'm saying is, I'm not interested in these other loops. There could be loops here too, you know, lots of loops. But I'm saying I'm not interested in that. I'm interested in one loop. Give me any loop you'd like. I know that one loop must exist. Why? 2 words. Pigeonhole principle. So take some loop, I don't care which, call it V. Could be lots of other loops, I don't care. And it doesn't hurt anything. Because that one loop V will be part of the string, and it will be part of the string that got recognized.
Oh.
And if it did, I can go around the loop twice, 3 times, 4 times, or 0 times. And they must all be in the language. There must be a pump. And pumping it up or down will still stay me in the language. It will leave me in the language. Shouldn't exit me out of the language. But it does, because the pump cannot be in the zeros, cannot be only in the ones, and it cannot cross the boundary between the two. So where will the pump be then? can't be anywhere. But it must be somewhere. That's a contradiction. So one of our assumptions is false.
So,
what assumption did I make?
That it's
That there's a finite automata that does the job. That's it. So there isn't.
So I think I misunderstood some of the part, but I don't know where. So I can have a pump in the zeros, and I can have a one. I can have another
So you
pump.
cannot have a pump in the zeros, because if you pump up the zeros and not the ones, there's too many zeros, not enough ones.
Can I have two pumps? One is in zero and one is in one pump simultaneously. Does that make sense?
Well, you could have lots of pumps, but I'm focused on one pump, and that pump must be somewhere, right? And each pump is independent.
Right.
Right? Let's say I have another pump. So call it V1 is one pump, and V2 is another pump.
Mm-hmm.
I can pump V1 independently of V2. I can pump V1 7 times and V2 13 times. I don't have to pump them in the same quantity, right?
Yeah.
So if there were two pumps, one in the zeros and one in the ones, I'll pump this one twice and this one 3 times. And then they're out of kilter again. Or you know what? I'll tell you what. I'll pump all the pumps 0 times and just pump this one once or twice. Because I can't pump something 0 times and stay in the language. So if you have other pumps, I get to choose how many times I pump it, not you. I get to choose. You're in a finite automata, and you must act in a certain way because of the pigeonhole principle. So I'll decide how many times you're going to follow each pump, and you must do that. How am I going to decide? By inserting extra V's for you to follow. And you must do that. You're a finite automata. You have no choice. You're deterministic. It's like Groundhog Day, the movie. Every time you must do the same thing every single day you wake up. How many know even what I'm talking about? Bill Murray? Okay, good movie. So, we just proved that 0 to the n, 1 to the n is not a regular language. That's a proof, a non-existence proof. We proved that no possible finite automata in the whole universe could possibly recognize that language. Even if you have a trillion state or a googolplex state, it's not enough. And that's a non-existence proof. We prove we're not millionaires. That's hard to do. Today is a good day. And we prove non-existence of something. Yeah.
Can U or W be null?
So, yes, U and W can be empty, but V cannot be empty and should not be empty. Because if V is the empty string, pumping it up is not going to buy you anything. And that's why we say that V has to have at least one character in it. Its size is bigger than 1. But U and W, those could be small.
Can you give us another example of how to pump, say for example, 0 power and 1 power and 2 power? To show how it's
Yeah,
not
but first let me say that I could have chosen n large enough, bigger the number of states in the machine, so that the pump would be forced to be in the zeros, and not even have a choice to be in the ones. How many understand that? And then I just have one case to wonder. V is only in the zeros because I make the zeros large enough that the zeros already will force the machine to cycle because of the pigeonhole principle, because there's more zeros than the number of states in the machine. So I don't even need to worry about the crossing the boundary or being in the ones for the pump V. So that can happen. And I can use the same argument for 0 to the n, 1 to the n, 2 to the n. Right? How? Take as many zeros as you want that are bigger than the size of your supposed finite automata that recognizes 0 to the n, 1 to the n, 2 to the n. And then you're cycling inside the zeros. The pump is in the zeros, nowhere else. And then pump off those zeros and you get more zeros and 1s and 2s by prediction. And the machine must accept all of them. Any other questions? So of course 0 to the n, 1 to the n, 2 to the n, 3 to the n is also not context. Or also 0 to the n, 1 to the n, 2 star. That's not context free either.
Right.
Or 0 to the n, 1 star, 2 to the n. Not context free also. All the same argument. Pick enough zeros that you then have to compare to ones. Make sure that there aren't too many zeros than states in the machine, so the pump is in the zeros. Pump it up, too many zeros. Not enough ones, but you must accept, but you shouldn't accept contradiction. So that language is not context-free either. So we just give a whole bunch of different examples. Just keep compounding it. 0 to the n, 1 to the n, WWR. Not context-free. So you can use it to show a lot of things not context-free. What you're basically saying is that the machine can't count. So that intuitively, it can't count to n reliably. There's not enough states. N could be arbitrarily large. The machine only has 73 states, or a trillion states, but trillion is a very small number compared to arbitrarily large n. That could be a googolplex, or a googolplex factorial, or some other huge number, right? But that formalizes the argument. It's one thing to say a machine can't count. Maybe you don't need to count. But this shows that there's no other way to do it except counting. And that's a formal proof. Just saying you can do it by counting and there's no way to count doesn't mean you can't do it without counting. How many get that? Okay, but this does say it formally. Okay. Now let me explain this piece of symbolic logic here. Now we understand the basic principle. He says that for every n large enough, n being an integer, there exists a string z in the language such that the string is bigger than n is this number in the pigeonhole principle larger than the number of states, such that there exists a u, a v, and a w in sigma star, which means they're strings, such that the string z of the input is equal to uvw, right? uvw. And the size of v is at least 1, so it's not trivial. Otherwise, pumping an empty string is not going to buy you anything extra. Such that uv to the iw is in L for all I. In other words, you can pump up the v to any exponent you'd like, and you must remain in the language. And that's what this says, what we just described over the last 10 minutes, with words and pictures. So, for every string large enough, you can break it up into 3 substrings, such as the middle string could be pumped up to arbitrary exponents and still leave you inside the language. That's what this says. But look at the quantifiers. There exists for all. There exists for all. So the quantifiers are nested 4 deep. There exists for all, there exists for all. There exists something such that for all something, there exists something else such that for all something else, something is true. That's 4 deep nested quantifiers. So don't let that confuse you. And keep in mind who gets to choose I and who gets to choose, the length of the string and so on. It's an adversarial argument. If you claim that you have a finite automata that can do this job, recognize 0 to the n, 1 to the n, then I get to choose a string large enough so that it forces you to cycle when you try to recognize it, so that then I can add extra middle pieces of that string that cycled you and force you to accept those too, but you shouldn't. And that's how I get you. That's playing gotcha. How do you understand that? Keep in mind our roles. You get to choose a finite automata, but I get to choose the string. You don't get to choose both. That's the nature of this argument. It's an adversarial argument. Okay. Any questions about it? It's subtle. It's a non-existence proof. It shows you the limits of what finite automata can and cannot do. They cannot accept arbitrary context-free languages. Can they accept any context-free languages? Finite automata? How many say, yeah, they can accept some context-free languages? Yeah, of course. Why didn't everyone just raise their hand? I'll ask again. Can finite automata accept any context-free languages? Good, that's better. What, for example?
Regular language.
All the regular languages, those are context-free. Why are regular languages automatically context-free? Recognizes a PDA that doesn't touch its stack. What's a PDA that doesn't touch its stack? Finite automata. Good. Now you're getting it. Any other questions so far? Yeah.
Well, is n considered deterministic with respect to closure?
What's considered deterministic?
The n, like
N? N is an integer, right? What do you
Yeah.
mean by n being deterministic? Are you saying 17 is deterministic and 23 is not? Or?
yes, I mean, like you can use n to represent any integer.
Yes.
But
N could be any integer. And I'm choosing to make it large enough to make this work. And the way to get it to be large enough is to make it larger than the number of states in some finite automata that supposedly accepts this language.
okay, so when you decide n, it's like a point. You select one specific n, specify that n. But closure is like it covers all.
Wait, the language is 0 to the n, 1 to the n, all n bigger than 0. That's the language.
Oh.
It's all strings of this form for all n together is the language that we're talking about. So they're all there for all n. But that brings an interesting point of potential confusion. Let me ask you a couple of questions, or all of you a couple of questions. Consider the string 0, or say A to the Google, B to the Google. There is a string, and Google A is followed by Google B. Very good. Let me ask you a question. Is this string regular?
Yes.
How many say yes? How many say this string is not regular? How many say this string is neither regular nor not regular because it's not even a language, much less a regular language or a non-regular language? Okay, gotcha. So you don't make type errors by saying it's regular. A string is not regular or not regular. Neither is a zebra, neither is my right shoe regular or not regular. It doesn't apply to these objects, to these types. A language could be regular or not regular, not a string. So it's a good thing you asked that question, because that caused me to ask this question, and you see most of the class got it wrong. They made a terrible type error. And remember I told you, try hard not to make type errors. Right? Don't call zebras regular. Don't call shoes odd or even. You can call integers odd or even, but not shoes, or vegetables or minerals. The types must match what you're talking about, right? So a string, this string is not regular. It's not even makes sense to say it's regular. Because it's a string. It's not a language. What if I put braces around it and make it a language? Now I can say, is this language containing this single string, A to the Google, B to the Google? Now you have one string language. Is this language now regular? This language with the braces around that string. How many say it's regular language? How many say it's not regular language? How many say it's a regular language? Good. I was waiting for most of you to raise your hand. Why is this now a regular language with braces around?
It's finite, so it can be represented.
It's a finite language. All finite languages are regular. Prove to me that all finite languages are regular. That's a separate thing. I don't know if we mentioned that explicitly, but it's pretty straightforward, so let's answer it now. Why are all finite languages regular automatically?
You can draw a DFA.
If I give you the language of all English words as strings, all valid English words. If you don't like this language, I'll give you the language of all Chinese words. All of them. Why is that a regular language? Pick any language you like.
Finite number of DFAs, every DFA for a single string.
But you need a single DFA, not a bunch of DFAs. What single DFA will accept the entire Chinese dictionary?
Can be finitely deep.
There'll be a big finite automata. How many can see that finite automata? Okay. How? Well, start at the start state somewhere, right? We'll use English, because my Chinese is not very good. So, have a bunch of states that, recognize the language, X. Okay? And then have some other states that recognize some other string in English, word in English, I don't know, boy, and so on and so on. For every for every word in the English language, I'll have a different path to a final state, and then I'll have, you know, a different path for every single word. There's about 1 million words in English, and I assume roughly 1 million words in Chinese, or characters, you know, represent words in Chinese. And this finite automata, taken as a whole, will recognize the entire English dictionary, or Chinese dictionary, or any other language dictionary, which makes that set of words or strings, you know, regular set. And I can do that with any finite set. There's nothing special about English or Chinese or German or Italian. They're all just finite sets of words. I'm not talking about whole sentences could be arbitrary at all. I'm talking about just valid words in the language. How do you get that? So we just proved that any finite set is regular. Any questions about that? Including that one with the Google A's and the Google B's. That was a finite set. A very long string, but only one string. There's a very simple finite automata that accepts it with a very long path from the start state to the end state. Any other questions or comments or thoughts so far, confusions? So we're proving a bunch of things in rapid succession. So, you know, we argued, so how do you prove that 0 to the n1 to the n2 to the n is not even context-free? So it turns out there's a pumping argument for context-free languages, just like we just showed a pumping argument for regular languages. It shows you certain things are not regular. There's an analogous pumping argument for context-free languages, and it's a grammar-based argument, and we won't show it here. It's a little bit subtle and more complicated than the pumping argument for the regular languages on the previous slide. It's grammar-based. Instead of being machine-based, it's grammar-based. But it also depends on the pigeonhole principle. And what you end up is 2 pumps, not one. So this goes back to multiple pumps. So you get 2 pumps that must go up with the same exponent in lockstep. And here you can't have 2 pumps that go up in the same lockstep exponent. Because if one pump was on the zeros and another one was on in the ones, the 2's will be left out as you pump up zeros and ones. If there was ones and 2's, the zeros will be left out, and so on. And if it crosses boundaries, things will get out of order the minute you pump it more than once. So I leave it up to you to look up the pumping argument or the pumping theorem for context-free languages in both grammars, and there's a pair of pumps, not just one pump. For extra credit, you tell me how it works. I think it's worth wasting an hour of class time on that. Although, you know, maybe we could do it in half an hour, but I'm not even sure it's worth half an hour at this point. Because this kind of pumping argument for regular language that we saw over here already tells you a lot of the subtleties and issues and ways to prove things are not in this class, namely regular and so on. But I'm just bringing to your attention there's a similar pumping argument for context-free languages. And next time we'll start with Turing machines. Now, there's a homework set or homework assignment due, I guess, a couple of weeks from last Friday. I'm soon going to post a lot more problem sets to the class website. Not homeworks, but problem sets, like I did the first problem set. There'll be 5 or 6 other problem sets. And there'll be lots and lots of problems on those sets, so you can solve lots of problems. The homeworks will all come from those sets. There'll be simple variations of problems from those sets. So will the exam questions. So you already know how I operate if you do my class last semester. There'll be problem sets, and all the exam questions, the midterm, the final, and even the homework questions will come from those problem sets. So you can solve them to your heart's content, and if you solve a lot of them, you walk into the final and the midterm, you would have seen everything before, you just write down your answer